Today we're going to continue with working on our Moody Diagram problems. We're going to discuss the different types of Moody Diagram problems that we have. And when I say Moody Diagram, really we're looking at pipe design problems. And some of these pipe design problems will require iterative solutions. Just as a bit of a review, we're taking a look at a pipe. So here we have a sketch of our pipe, and it's got a rough wall. To follow the notation in the textbook, epsilon is going to be our equivalent roughness, and we're going to have this equivalent roughness really comes from the definition that was given by Nicorazzi, who was, I guess he's from Georgia, the country of Georgia, and ended up being a German scientist, spending his life there. And he studied roughness effects on pipe flow by gluing sand grains into pipes and then doing the experiments on it to determine the pressure drops. Anyways, that's what the equivalent roughness is. And just to be careful, this equivalent roughness is not the roughness that you would actually measure under a microscope looking at the height, but in fact is more of a fluid dynamics effective roughness. And they're tabulated, and so that's important to recognize. And so back here, as we talked about in last class, you have from your textbook, you have this table 8.1 if I recall. And table 8.1 shows you different types of equivalent roughnesses in both feet and in millimeters. So be careful, you use it as in millimeters, not in meters, for different really important materials. Like you have here riveted steel, concrete, for example, if you're doing pipes with water flowing through them, maybe wood, stave, cast iron, etc., down to these are relatively rough surfaces that we have up here, but on the bottom we have things that are quite smooth, like commercial steel, drawn tubing, or plastic and glass, which is considered smooth, in which case, if it's considered smooth, if we go back to our Moody diagram, that's going to go along this smooth curve that we have here that forms the bottom. Just a few more things that I want to talk about with the Moody diagram itself. Now, just to remind ourselves, this is the friction factor, or the Darcy, or sometimes called Darcy-Weisbach friction factor, as a function of the Reynolds number. And we have our laminar flow region that's from 0 to about 2,000. And then beyond this dashed line, we have this wholly turbulent region. And in this region here, inertial effects dominate over viscous effects. And so there's not much there's an effect of the roughness length itself, because that is going to, as we increase the roughness, that's going to increase the pressure drop. But in addition to the roughness effect, the Reynolds number is no longer important. That region is constant. That region has a friction factor that is constant with Reynolds number. Now, the other piece that's important to look at is this middle region. Between a Reynolds number of about, say, 2,000 to 4,000, where these vertical lines exist, that region in here, this region is where this Moody diagram is pretty poor, and this is where we're transitioning between turbulent, and so transition between turbulent flow, from laminar, so transition from laminar to turbulent. And the flow could have characteristics of either or both, and that region makes it very, very difficult to design in. And in fact, if you can avoid designing in that area, that's optimal, because you're not sure always what you're going to get, because it could depend on a number of factors that you have. So this transition regime is usually you try to avoid. Once you get beyond the transition regime, this is going to, and the flow is turbulent, but it's still turbulent, but there's some effects of, there's a balance between viscous and inertial effects. We see that we have this reduction, that is there's a function of the Reynolds number that occurs between 4,000 and this dashed line that represents the wholly turbulent flow. And so in there, we have quite a bit of variability of in that region we have variability of the friction factor with Reynolds number for different roughnesses. So just kind of mental note. And the Colebrook equation that I talked about last class, which is in the textbook, that's going to be valid for anywhere above a Reynolds number of about 4,000. So Colebrook equation That's that transcendental equation, which means that it's iterative. You have the friction factor on both sides, and that is a little bit of a pain, but that's where it's valid. In fact, this diagram, these lines are produced from that Colebrook equation. All right, so given that sort of bit of a review and reminder, I would like to talk about some of the different types of Moody diagram problems that we have. And so let's go through them one at a time. The first is basically what we did last class, and it's the most straightforward. So it's going to be type 1. In type 1 case, we would say that we have the length. And again, I'm going to use these same definitions for our pipe flow that we have over here. So the length of pipe, diameter D, length L, velocity V, and roughness epsilon. And of course, the viscosity mu, dynamic viscosity mu, and the fluid density rho. So we're going to assume usually that we know the fluid, and if we say, and we're usually going to know what the pipe material is. In such a case, we'll know what the roughness is. So in all of these cases, let's assume that we know, let's see, there you go, using that again. Let's assume that we know epsilon and fluid type. And what we don't know, say for example, we in addition to those two parameters, we'll know the length, say the flow rate, the diameter of the pipe. These are all known. So length, flow rate, diameter, or it could be length, velocity, average velocity and diameter. And we want to find delta P. So that's our unknown. That's the kind of problem that we've already done. So in such a case, step 1, we go ahead and calculate the Reynolds number, and E over, and epsilon over D, our relative roughness. Now, once we know the Reynolds number and the relative roughness, we can go calculate our friction factor from the Moody diagram or from the Colebrook. So this is from Moody or Colebrook equation, or whatever equation that you choose to use, because there are some of the simplified ones. Once we have F, we can go right away and calculate our major head losses, and that's going to be equal to, as before, the friction factor times L over D, V squared over 2G. Or we can write that as a pressure drop, as you can recall, and the pressure drop is, in the energy equation, is delta P over rho G, and that's equal to FL over D, V squared over 2G. So we can right away calculate the pressure drop from that. So that's going to be simply delta P equal to rho F L over D, V squared over 2G. Or the other way that we could write this as this is also going to be equal to H, our head loss, times rho G, because this is equal to the head loss that we have here. So same idea. These are the basic equations, and it's straightforward. There's no iteration required. So this one, no iteration required. And that's what we did for the example in the previous lecture. Our next type that we're going to look at, say for example, so type 2, and your textbook lists them a little bit differently, but it's basically the same concept. We're going to know the pressure drop. We're going to know the flow rate or average velocity and the geometry of the pipe, because we'll know D, the diameter. These are known. So pressure drop, flow rate, and diameter. And we want to design for L. So the length of the pipe is unknown. In this case, what we're going to do is we'll start by calculating. So we know Q and D, so we can calculate. So one, calculate, as you can imagine, the Reynolds number based on the diameter. And as before, we have the relative roughness. Knowing those two things, we can get F again, directly, the friction factor directly from the Moody diagram or from Colebrook equation. And now what we need to do is, well, since we're looking for L, what we can do is, given that we know what the pressure drop is, that is, we know what the head loss is, remember that that's equal to FL over D, V squared over 2G. So in this case, what do we know? We know the pressure drop, the head loss, that's exactly equal to the head loss times rho G, just like we had up above. And given that we know our, again, we can write this as delta P over rho G. So we can think about it as solving for delta P or HL. Both are the pressure drop, essentially. One is in the terms of head loss, the other is in terms of pascals, say, for example, or pressure. So we've just calculated the friction factor. We'll know that. We know the head loss or the pressure. We know the diameter, and we know the average velocity in the pipe. So we can go ahead and solve for L. So solve for L. And in that case, we end up with L being equal to the diameter times our head loss, again our major head loss being the pipe, that's what we're talking about, times 2G over FV squared. Okay, so then this is how we get our length. So up here, this was the pressure, and here we have our length for this type. So again, this one's pretty straightforward. Again, you're always going to be taking advantage of the fact that you know that the velocity is equal to the flow rate over the area from conservation of mass. And since you know the diameter of the pipe, you'll have the area that you can calculate. For type 3, in this case, again, we're going to know delta P. We'll know the length of the pipe and the diameter. These are known. But our flow rate's unknown. Q is unknown. Now, how are we going to do this one? This one's a little bit trickier, but not too bad. What we'll do is, one, we're going to get the velocity in terms of the friction factor. So get V in terms of F. So how do we do that? We can go back up to here. We're going to use this, our simplified version of the energy equation. So if we know, we'll either know, since we say have the pressure drop, we'll either know the head loss or the pressure drop, and we can solve for V instead of, here we solve, in this equation we solve for L, but now we could also solve for V. And so if we solve that for V, then we now have a velocity that we can use. That's step one. Then the next thing that we're going to do is we're going to guess a Reynolds number. Okay, we don't know what the velocity is, right? So we're going to guess a Reynolds number. And we're going to guess usually in the fully rough zone. Or what we also talked about, the wholly turbulent zone. This is where the Reynolds, or the friction factor, is not a function of the Reynolds number. This is this flat line part that we have here. So you know what the roughness is, so you can say if your roughness was 0.05, then you would just guess the you would guess a Reynolds number here at 0.05, and then go all the way across, and then say, okay, well, it's a little over 0.07, maybe 0.071 in that case. So what we're doing here is just guessing, and it's a very logical guess, because you can see that for a lot of pipe roughnesses, most of the friction factors correspond to the wholly turbulent zone. So that's our first step, our second step. So first step, calculate velocity in terms of the friction factor. Next, guess a Reynolds number based on the relative roughness. So guess RE based on the relative roughness in the fully turbulent zone. Then once we have that guessed roughness and friction factor, we can take so then we can plug the friction factor into our velocity equation, the one that from step one. And once we have that velocity equation from step one and the friction factor in there, we get a velocity, so solve for that v, so solve for v, and then substitute that into the Reynolds number, which is Vd over nu. We know d, we know nu, and now we have a newly calculated velocity. So given that new Reynolds number, we can go ahead and use new Reynolds number to compute new friction factor. And we can do this step by step. So then now that I have a new friction factor, my next step would be compute new v, new velocity. Again, every time we have a friction factor, we plug it into our step 1 where we computed the velocity. So here we're doing it again. And so now that we have a new velocity that we have, then we do Reynolds number. Now we have a new Reynolds number. That gives us a friction factor, and then velocity again. And once we have a velocity, we can go back up. So this is our iterative process, and we continue until the friction factor, until F, doesn't change much. And that, how much it changes and how long you'll continue to do it is going to be based on the problem at hand. And we'll do an example like this. Okay, so that's type 3. Then the last type that we'll talk about here, type 4. Another iterative problem type. We will know the pressure drop, the length of the pipe, and the flow rate. These guys are known. And the diameter of the pipe is unknown. So this is a design problem given some parameters related to the pressure drop, length, and flow rate. Now we want to know what diameter to choose. And say, again, the pressure drop that you're given is some specified pressure drop. So we'll call this the specified pressure drop, or delta P SP. So now what we're going to do is, our first step is to guess a diameter, d. And once I have the diameter d, I can calculate the Reynolds number, because we know q, which means we know the velocity. Once we know q, we can calculate the Reynolds number. And with the Reynolds number and epsilon over d, then we can calculate a friction factor. Given the friction factor, we can go ahead and calculate, so step 2, once I have that friction factor, and again, that's coming from the Moody diagram, same steps, we can calculate delta P. So, okay, I have a delta P that I've calculated, and that, remember, is just simply the FL over d, v squared over 2g, and, rho in there. And once we have that delta P, and we've multiplied by rho g, right? So we're using the equation that I gave you right here, which is the energy equation, delta P over rho g. I'm just multiplying both sides by rho g, and this g down here cancels, and then there's a rho in there. So we have delta P equal rho v squared FL over d. So we calculate our pressure in this manner, and if our delta P calculated is greater than that's not a very good greater than symbol, greater than the delta P that we've specified in the design problem, then we're going to increase the diameter d. So what that means is it's a design problem for the diameter, but we know that the pressure drop increases as we decrease the pressure drop increases as we decrease the diameter, so it's inversely proportional. So as a result, we're going to guess a diameter that's bigger and increase it and then continue to iterate. If, however, the delta P that we calculate is less than the specified pressure gradient, then we're going to decrease our diameter. Okay, so after doing these steps, then we'll go ahead and recompute the Reynolds number based on the diameter, then calculate the friction factor, and then we can continue to do this process. We'll calculate the pressure drop, see if it's bigger or smaller, and then continue on. And so this is a second iterative type of problem. So let's kind of put these together. So type 1 and type 2 were non-iterative. So non-iterative, and type 2 non-iterative. In this case, we were able to just calculate from known variables. Type 3, however, this was iterative. This one was the case where we know the pressure drop, length, and diameter, and we want the flow rate. And then type 4, this is iterative as well. All right, so now that we've walked through all of these, let's do an example, because I think that will sort of set things straight. So example. This is an iterative Moody diagram problem. So that is, we're doing some kind of pipe design. So piping system design. All right, I'm given a pipe. It has some length. The length that we've been told on our piece of pipe is a big L, and that's going to be equal to 100 meters. And we have been told that the pressure drop across that, the H, our major loss, again, this is only piping, is equal to 8 meters. So our pressure drop, our head loss, is 8 meters. The material is oil, and it has a density equal to 950 kilograms per meter cubed, and it has a dynamic viscosity of 2 times 10 to the negative 5th meters squared per second. We're also told that the diameter here that we have of the pipe, D, that guy is going to be equal to 30 centimeters. All right, so let's think about what we have here. Ultimately, we are asked to find the flow rate in the pipe. So find Q in the pipe. So we're going to be looking at trying to find our flow rate. So what is unknown is the Q. What's known, okay, we know the pressure drop, we know that's our head loss, we know the length of the pipe, and we know the diameter. So delta P, L, and D are known, but Q is unknown. So delta P, L, and D are known. So that means that we're going to move up to our type 3 problem. So delta P, L, and D are known, but Q is unknown. So this would be a type 3 iterative problem. So this is a type 3 iterative problem. So if you recall, this step means that we're going to need to get the velocity in terms of the friction factor, guess our Reynolds number, probably in that fully rough-in area, and then our wholly turbulent regime, and then we're going to go ahead and grab a Reynolds number and iterate. So step 1, we have that the head loss that we have is equal to delta P over rho G. And again, this is equal to FL over D, V squared over 2g. Okay, this is our basic equation. What equation is this? This is the energy equation. So let's solve for the average. Let's put the bar there for the average velocity for v bar. And if we do that, we'll have that v bar is going to be equal to square root of, so I have HL, which is our major loss, times 2g, and that's also times the diameter, which is in the denominator over there, divided by FL. Okay, so we've gone ahead and just solve, we'll say, call that equation star. We solve star for V bar. All right, now that we know what that V bar is, we can go ahead and we'll go ahead and use this equation to determine our velocities that we're looking for and ultimately our flow rate. So what is this? Let's see. Well, we know here the head loss was defined up above as 8 meters. So 8 meters times 2 times gravity, 9.8 meters per second squared, times the diameter of the pipe, which was 30 centimeters, 0.3 meters. And then we have our friction factor, which we don't know, but we do know the length of the pipe. That was 100 meters. And so our equation that we're going to be using to iterate on will solve this. If you plug it in, when I did this, I got 0.0471 meters squared per second squared divided by F. And that should unit-wise make sense because the friction factor is non-dimensional, and it's a non-dimensional parameter, it's a pi parameter, and so the square root of meters squared per second squared will give us the velocity, which is in meters per second. Okay, so we'll use that basic equation. Let's simplify it one more, take the square root of it, why not? 0.686 meters per second divided by the square root of the friction factor. So we use this equation. All right, so as I said before, let's go ahead. Step one, we're going to guess our Reynolds number, and it's going to be in the wholly turbulent regime. And then we'll get a friction factor from that. Okay, so how do we do that? Well, we have to have some idea of what our roughness is. And so backing up back here in our problem, we are told that the relative roughness, epsilon over d, is equal to 0.0002. Okay, so 0.0002 is part of the problem statement. So epsilon over d is 0.0002. So what we can do is we can go back up here to our Moody diagram. Where'd it go? Here it is, and find 0.0002. That's over here, and I'm going to draw a line somehow across here. And hopefully it's, I think that's straight. That's going across, and if we have, it's a little less than 0.05, so let's see what we have, 0.01, 0.02, 0.03, 0.01, 0.0, and these are 0.01, and then the value that it attains, so 0.01, 0.012, 0.013, and then we have 0.014 and 0.015. So we have a value that we're looking at here that's pretty, it's just less than 0.015, and that step below it is going to give us a value of about 0.0135, just about maybe 0.014, we could say. All right, so we found F is about, oops, I gotta go down even farther. F is approximately, so from Moody, F is about 0.01. And when I did it more carefully and slowly, I get 0.0135. So I maybe moved my line up just a bit and not perfectly straight, so I apologize there. So to compute it, the velocity, we just plug that into our equation, 0.686 meters per second divided by the square root of our 0.0135 that we had from the Moody diagram, and that is 5.9 meters per second that we get. All right, now what's our next step? So the first step we had was to calculate, so get V in terms of F. We did this, we guessed a Reynolds number and used our relative roughness to get a friction factor. And then we plugged in the friction factor into the velocity equation to get a velocity. And now what we're going to do is we're going to calculate a new Reynolds number. So let's go back and do that. So calculate. So we guessed our Reynolds number, compute V, and now we're going to compute the Reynolds number again. Well, I guess for us, this is the first time. So this is going to be 5.9 meters per second times our diameter, which is 0.3 meters, divided by our viscosity, which we were told for this oil, excuse me, is 2 times 10 to the negative fifth meters squared per second. And if we compute that out, I get 88,562, which is about 8.8 times 10 to the fourth. Or we could say 8.9 times 10 to the fourth. It doesn't, oops. In our Moody diagram isn't so precise. If we use the Colebrook equation, we would directly put in the 88,562. All right, so let's go take a look back at our Moody diagram and see what that would give us. So we said that we had a Reynolds number of 8.8, or about a little less than 9 times 10 to the fourth. So this is 10 to the fourth. So that's here we have 1 times 10 to the fourth, 2 times 10 to the fourth, 4 times 10 to the fourth. Up here, this is 8 times 10 to the fourth, and then that little line here now, we're going to have 9 times 10 to the fourth here. And so if I bring that up and hopefully keep it straight, not as well as I did before, that's going to continue up. Continue up here. And now we have to follow our appropriate line that we started with. So remember, our roughness is 0.002 over here. So now instead of going straight out in the wholly roughened zone, we're going to follow this up to about here, and then go across. Hopefully I get a straight line here to approximately here. It's not perfect, but it's just, and I think my line is a little bit low here. Let's move it up just a little bit. Redo it. I apologize here. You can see that this kind of intersects just a little. Oh boy. Undo. Uh-oh. That's not good. Okay, so I'm going to redo this. So we get rid of our material here, delete, and we'll redo it again for those of you who hate me. I apologize. So 0.002 is our relative roughness. We're coming across like this, and that obviously is our 0.002. And yeah, that now we see better that this is here, this is 0.0313 and this is 0.014, and the straight line is much better represented as 0.0135 for our first step. We came over here and we looked at our Reynolds number that we were looking for, which was about 9 times 10 to the fourth, just under that, and move that back just a little bit. That's not quite straight. Let's do it again. 9 times 10 to the fourth. And that's pretty close, like this. And we could go again and follow our line to about here. And from about here, we can go out horizontally. And we're between 0.08 and 0.019 and 0.02. So let's call that right there 0.0195. So 0.0195, approximately. It's about halfway in between. It's obviously not perfect. Sorry, there's a 0.0195. Right, just through that. So we'll come back down. We have 0.0195 for our new friction factor. And I keep putting it in the wrong spot. Copy that guy. Back down to our problem. Okay, so here we have the friction factor, and we got that again from Moody. All right, so given that friction factor, we can now recalculate our velocity. So we have the average velocity equal to the 0.686 meters per second divided by the square root of our friction factor. That's our equation. 0.68 divided by now 0.0195. And you can see what we had before. This was our up above. This is where we had 5.9 meters per second. Now if we plug in the value of 0.686 divided by the square root of 0.0195, we get a velocity of 4.95 meters per second. And so it's lower. And so we can continue this process until we iterate. Usually, for an exam, I will give you a specified number of iterations to do. Probably it'll just be one for an exam, and that's because then you can show me that you understand the procedure. Usually, we implement this iterative procedure in a MATLAB code. Iterative procedure in a computer code. Whatever this could be, MATLAB or Python, whatever, C++, your favorite flavor. But you can see very quickly it's a very simple procedure, and in order to do that implementation, we also will use the Colebrook equation instead of the Moody diagram. So with Colebrook equation, sometimes called the Colebrook-White equation, but Colebrook equation. That way you can do the iteration automatically. But note, when you do it with the Colebrook equation, you actually have to iterate two ways. You have to iterate, as we're doing right now, for the friction factor, but then to actually compute the friction factor, since it's a transcendental equation, you have it on both sides. So it's not a trivial calculation to do. So we now have our average velocity. So that's 4.9. So our average velocity is 4.95 meters per second. And we were actually asked to compute the flow rate. So our flow rate Q is going to be equal to our average velocity times the area. So that's going to be the velocity times pi times d squared over 4, or 4.95 meters per second times pi times 0.3 meters squared over 4. And I get a flow rate of about 0.343 cubic meters per second. So that's the flow rate that we have. Now, as just a little bit of in a side that we have here, the when we're thinking about the relationship between Q, the flow rate, and the pressure, our delta P here, so let's say this little aside, our pressure relationship that we have, delta P over rho is equal to FL over D V squared over 2. This is, so you could put G's in there as we had, so you could put a G here and here. This is what we've been using for our simplified energy equation. But as we just saw a second ago, we know that, of course, that Q is equal to V times A, and therefore the average velocity is equal to Q over A. And typically, so what we can do is then write this equation, our delta P, and if we do it, go ahead and cancel out those G's and multiply both sides by rho, we'll have rho times F times L over D V bar squared over 2. This is our pressure drop. What we can do is we can substitute the flow rate in here, which is a convenient thing to do. So sometimes we just, instead of first calculating the velocity and then doing the flow rate, we can just do the flow rate immediately. So we'll have rho times the friction factor L over D and times 1/2, and now we'll have Q squared over A squared. And since for a pipe, for a circular pipe, we have that the area is just pi d squared over 4 like we just computed, then we can substitute the area in. So we'll have delta P equal to 1/2 rho FL over D Q squared, and now we'll have in the denominator, so we'll have pi squared, so we're going to square this over here, so we'll have pi squared d to the 4th, and then we have a 4 squared in the numerator, so we can multiply that by 16, and that's 4 squared, and so then we can cancel out the 16 with the 2, and that becomes 8, and our delta PQ relationship here is delta P is simply 8 times rho F L over D, and then we have the Q squared divided by D to the 4th times pi squared. So this is a nice simplified way to go back and forth from pressure to flow rate. Something that you could certainly do however you might like, either way. But this equation makes it kind of easier to work forward with. One of the things that we typically want to talk about in addition to this kind of a problem, we've talked all about major losses. So let's ask the question now, what about our minor losses? I'm going to spend very little time on this because we did a couple problems on this already. So remember that we have our head loss total is equal to the head loss major plus our head loss minor. And remember the units of these are all height or meters. And when we talk about minor losses, we're talking about things like fittings, bends, and valves. And if we go back to our PowerPoint here, here we're talking about minor losses. So as before, we have this equation for the minor losses for the head loss. That is, we have some coefficient, loss coefficient K times V squared over 2G. And when we see these different losses that are always occurring when you have turbulence, and I mentioned that before. So at the entry, say for example, where flow separates, and then we have turbulence here, this is usually associated with the dissipation of kinetic energy. That is, we're ultimately taking velocity or kinetic energy of the mean flow, and we're dissipating that into heat. We're losing some of that energy, and as a result, it's going to be manifesting itself in a pressure drop. So these different types of entryways, so this one kind of penetrates in, this is a sharp edge that we have here. This is an edge that's a little bit more rounded, and you can see there's, as we move step by step from 1 to 2, we get a little bit different and less separation. 3, we have much less separation and less dissipation. But if we really round that entry region, we don't have a separation region, and so our frictional factor and our losses actually can go to 0 if it's very smoothly done. Over here on the left, there's an example of flow going through a valve, which is another type of minor loss. And we have, as this flow has to, the streamlines try to go through here, you can see that they separate and there's significant turbulence in this region. that is leading to dissipation of energy, of kinetic energy. And as a result, our losses that we need to account for that increase our pressure drop across this kind of a device. So some of the, one last thing I want to point out that's really important over here is this curve that we have. So the, and you can look and say this is minor losses, this on the left-hand side, this plot of minor losses is a function of velocity. You can see that the equation shows that we have a parabolic type of a profile. That is that the pressure drop increases with velocity in a squared manner. And so this is going to be important because you can see that at relatively low velocities, the pressure loss is very small, but as we move up, it rapidly, because it's quadratic, it rapidly increases. And there's something to keep in mind with your problems. The other thing to recognize is that this is just rewriting it, we know that delta P over rho G is equal to K L V squared over 2G. So we could write that as this is equal to our head loss minor that we have in this case. Maybe say delta P minor just so that we know that. So we could multiply both sides by gravity here, and then I'll get rid of this, but multiply both sides by gravity and then multiply by density. And so the delta P minor head loss is the pressure drop minor in pascals is rho times our loss coefficient times v squared over 2. Looking at some of the different behaviors, so on the top left that we have here, we're going from, this is a sudden expansion, we call it. And in a sudden expansion, if the area 1 is much smaller than area 2, so you can see that this is the loss coefficient as the function of the area ratio. When that area ratio is very big, when that area ratio is very small, so A1 over A2, when it's A1 is much, much smaller than A2, this goes to 0, which means we move to the left-hand side of the plot, and our loss coefficient is big. As A1 over A2 becomes the same, equal to about 1, then you just, instead of having, you don't ever actually have a expansion, and so that loss goes to 0. That is, we're only left with losses that are major losses. Here we have some other types of situations. So what if we have a bend in a pipe here? You can see that the flow separates on the bend, and also secondary circulations start to form. And as a result, for different roughness, relative roughnesses, we're going to get different amounts of loss for our loss coefficient. And then similarly, this is another type of expansion. This is more of a diffuser, where we have an angle that expands a little bit more gently, and it's a more complicated curve that we have, and this is non-dimensionalized, and it's a function of that angle. But here, given that fixed area ratio, we have different functions of KL that we can find. And actually, as this angle theta gets bigger and bigger, it gets sharper and sharper, and the losses get to be bigger and bigger. As theta gets smaller, the losses tend to be on the smaller side. Your textbook also has different aspects, like different standard piping things. So here's a 90-degree elbow, 45-degree elbow, return elbow, T's of different types, and from that you have all of these different loss coefficients that you can use to do your computations with. So hopefully you'll continue to move forward and practice some of those types of problems. All right, so let's talk about pumps for a minute. So pumps and system curves. So here, this is a delta P versus Q plot, and it represents a very simple system that I've drawn below. So I have a pipe, a pump, a pipe, and then a valve. All right, so if I were to, my system is merely made up, and let's say that this kind of connects back together. So my system is going to be pipe plus valve. So if I wanted to calculate the head loss associated with that, I would have, so the head loss total would be equal to the head loss major for all of the the whole length of the pipe plus the head loss minor due to the valve. So we can sum, if we have a pipe parts in series, we can sum the different head losses to get the total pipe pressure drop. But then we also have a pressure drop for our a pump. The pump actually, it's not a pressure drop, but the pump increases the energy, the flow energy, and it raises the pressure, and it depends on the flow rate. So how does it depend on the flow rate? Well, I've sketched a typical pump curve here, which has maximum pressure drop at 0 flow rate, and it has a minimum pressure drop when there is no, at maximum flow rate. So what ends up happening, let's think about that physically. So what is 0 flow rate? Well, that means if I turn my valve to 0, there's no flow going through the pump. It's stopped. And so it's working really, really hard and has a very low pressure at the inlet, and then it's being stopped at the top, so there's a high pressure. So that is represented by this part right here. That's where the pump is basically completely blocked. And if I take the valve out entirely and there's no, basically we just have no resistance, then I'm down here, and that's where the maximum flow rate is. There's no resistance, and so the pressure drop across the pump is 0. And so what is that? We can kind of talk about that a little bit more quantitatively. And let's go back to here. So this is pumps and our energy equation. So where does that come from? If we have our classical energy equation, so W dot shaft, we have that because it's a pump, and that's going to be equal to our m dot times P1. And so normally we divide this by m dot times G, but I'm multiplying it by m dot, both sides of the equation by m dot times G. So I have alpha V1 squared over 2 plus GZ1, we'll call that the inlet, minus, and just put a big bracket so I don't have to draw the m dot again. So all right, our exit, that's going to be the second point, so P2 alpha squared over alpha V2 squared over 2 plus GZ2, so that's at our outlet. A little bit redundant, but it's okay. That we have here, because this is our basic equation, and if we think about it, if we have one inlet, one outlet, and that will, and it's horizontal, so that is Z1 and Z2 are equal to one another, so we have the inlet and outlet at basically the same height. If that's the case, then inlet and outlet, same heights, these cancel out. And if we have one inlet, one outlet that are of the same diameter, in that case, so then same inlet exit diameter, then conservation of mass will tell us that V1 bar is going to be equal to V2 bar, and then let's assume that just alpha is equal to 1 for the moment. And sometimes this doesn't work out, but these guys cancel out. And so our pump, our shaft work, ends up being our delta W dot. And this is, we'll just call it pump, because that's what this is in this case. It's going to be equal to the m dot times our delta P, P1 minus P2 over rho. And that's our the pump, the power of the pump that we're looking at. So this is in watts. It's the pump power. So just for a second, if we briefly go back to the figure from the PowerPoint, you can see that actually really quickly we can determine the pump power from this curve. If we have this red line being our pump curve, then if I know I have this pressure drop and this flow rate here, then I can calculate the power here. This is going to be my pump power, or work rate, is simply going to be equal to the m dot times delta P across the pump over rho. And then if we kind of think about what this is, it's a simplification, right? So m dot is simply equal to rho times Q delta P over rho. So that power for the pump, cancel these guys out, is equal to Q times delta P. So it's kind of nice. We can get the power from the product of the flow rate times the delta P. So this is directly from the energy equation. So this, let's go ahead and resubstitute this in here. So the pump power is going to be equal to rho times Q delta P over rho, which is equal to Q times delta P. All right, so this is an important equation that we're going to be that you're going to want to use and remember going into the future. Now, going back to our pump system, the next thing that we might want to think about here is what about so we've looked at the pump curve. Now, I showed you how the head loss curve behaves. If we go back to here, head loss behaves for minor losses like KL v squared over 2G. And if you remember for the pipe, what does that do? What is the major loss? That's F L over D v squared over 2G. So they both behave as a power of v squared over 2G. So our system curves that we're going to put together, which is going to be basically plotting the head loss total, is going to be the head loss major plus the head loss minor. They all have terms that look like v squared over 2G in them. This one's like, this is an FL over D, and then this over here is a KV squared over 2G. So they're all going to be a quadratic power loss. So here's an example. This is going to be the system curve. And this is really important because you can calculate, if you're given a pump curve, which is given by the manufacturer, or you can develop it on your own, then what we have is what's called the operating point. And that's where the two curves cross each other. That is, this green curve and the red curve cross each other, and that is where the pump will function. You don't really have a choice. But this is for a particular valve setting. So you do have a choice in the sense that if you can adjust the valve. So what does that effectively do? There's our operating point and system curve. If we close the valve, that's effectively like, and it's going to increase our loss coefficient, and it's going to move our curve here, our system curve, to the left. And that makes sense because as we close the valve, we're going to increase the pressure, some amount, delta P, across the valve, because we'll have more of a pressure loss. And as we close the valve, that's going to cause a bigger pressure drop over the across the pump, and so we move the curve in this direction. So if I want to operate here, I close the valve. The other thing I can do to adjust where I operate here is I can buy another pump that is variable speed. So in this case, now I've got the same original system curve, but now I have a variable speed pump. And so if I reduce the pump speed, I can move it down here. So I can, instead of operating here, I can now operate here. And then I can do similar things where I continuously, say, decrease the speed or increase the speed, or I close the valve, or I open the valve. So it gives me a range of places that I can operate. So the only place that I can operate are where these two curves cross one another. And usually what we end up doing then is saying, okay, the operating range, what is the efficiency of the pump in that area? And most of the time, so pump manufacturers will provide curves for this. Okay, so that kind of covers the pumps, and it's really important. If you want to take a class in thermal system design, we cover this kind of a lot more, or the HVAC class. And I highly recommend those two for getting more information about this, because there's lots of things we haven't talked about. Say, for example, different types of pumps, different types of how we deal with different types of pipes, whether it's pipes versus tubes, how they're specified on their diameter. There's a lot of things that are sort of engineering basics that you can learn and look up, but we don't have time to fully cover in this class. The last thing I want to do is remind you about two different types of piping systems. So far we've been talking about pipes in series. And in pipes in series, if we have here, say, a diameter D1, which is wider, and then it gets smaller and smaller, what we know is that the Q here is equal to the Q here, and it's equal to the Q here. And so we'll call that, say, Q1, Q2, and Q3. The pipe flow rates are the same, because if we did our mass balance, they'll be the same across. And we know that we'll have a head loss associated with here. Call that head loss 1, head loss 2, and head loss 3. Then for in series, we can sum those together to get the total head loss. For systems in parallel, and I won't do too much of this, but it's really important for you to recognize it, because this is kind of a lot like circuits in series and parallel. And here what we have is, say that this pressure is constant, P1, and this pressure down here, P2, roughly. We're going to have a situation where these guys are, instead of the pressure being added across it, the pressure, the delta P, is equal. And what we have is flow rates that are going to vary. So delta P across 1 is equal to delta P across 2, which is equal to delta P across 3. For water, it's not exactly correct, because we have a little bit of this height difference that we have to deal with. But let's think of it maybe as two air reservoirs where they would be identical in the amount of, maybe it's compressed air that you're moving through this pipe. With water, you have to count a little bit for that difference in head. Let's say it's small for the moment. But then the flow rates are going to now be different in each of these, because we have different diameters. So we have to adjust for that. So when we talked about originally this difference between a pipe in series, where we're going to sum the pressure drops here, now what we'll have is all of the pressures are the same in the parallel system, and the flow rates then are going to sum up for us. So as an example, I have my textbook here, and of course, since I don't have this on my video, but if we go to chapter 8, I highly recommend you guys taking a look at this. It's, again, the parallel piping networks are a little bit more complicated, but not much more, and they're pretty typical in real piping systems. So if we have, sometimes we'll call these pipe networks, and so this is in chapter 8, and chapter 8, this is section 8.5.2. I think it's pretty important to look at this, and so it reviews exactly what I just said, and that is that that we have the flow rates being equal for a series pipe, and that we add our pressure drops for pipes in series, and that our pressure drops are equal in a parallel pipes, and that the total flow rate is just the sum of the other flow rates. So I highly recommend just taking a quick look at this, because it's something that often is used, and it'll help you with problems in the future. Okay, I think that will be it for today. Go ahead and do the homework that is supplied for Tuesday, and then I'm also planning to give a quiz on Tuesday, but I'll post that announcement as well. Thank you.